These are your 5.1 notes, and we're going to start looking at probability, and we're going to start just with the basics of randomness, probability, and simulation. So first of all, we want to talk about chance behavior predictability. Chance behavior is unpredictable in the short run, but has a regular and predictable pattern in the long run. So this concept forms the basis for the idea of probability. Easiest way to think about this is things that are like highly based in probability, that are like purely chance-based things. So whenever you hear somebody talk about like Vegas or going to a casino, those are games of chance. So like roulette, craps, roulette and craps especially. I'm kind of blanking on all my others because like blackjack and poker are also slightly game of chance, but there is a little bit of skill. There's a little bit more that can be based in like reading human persona there. Like slot machines to a certain extent, like all of these have like high chance behaviors. Rolling a dice is a chance behavior. Flipping a coin is a chance behavior. Fair coins, fair dice, things that aren't weighted, they give you fair results. And chance behavior is unpredictable in the short run, but has a regular and predictable pattern in the long run. And this concept forms the basis for the idea of probability. So what do I mean where it's unpredictable in the short run? Well, that means if I flip a coin, there's like a 50% chance that it's going to hit heads or tails. And like theoretically speaking, I could flip 10 straight heads. That doesn't seem likely, and a lot of people are going to argue that like that's impossible. You can't flip 10 straight heads. Like the law of probability is going to dictate that if you flip a coin 10 times, it's going to fall on heads 5 times, it's going to fall on tails 5 times. Like that's just the way it has to work. But that's not in fact the case. Every single time you flip a coin, there's a 50% chance of it landing on heads or tails. And because every single time, like I flip a coin once, it lands on heads. The next time I flip a coin, it's not like the coin has this weird thought process to itself where it's like, oh, I landed on heads last time, so I have to land on tails. It's literally just chance. It could land on heads again. It could keep landing on heads. And it could land on heads forever and ever and ever. Now, if I flip a coin 10,000 times, I'm going to expect roughly 5,000 of them to be heads and roughly 5,000 of them to be tails. I'm not thinking about them in terms of, I'm saying roughly, like if one's at 4,985 and one's at 5,015, like that's close enough where it's roughly still 50-50. The chances of it being perfectly 50-50 are still low, even at those large numbers. We're just going to get closer to those values. And we can see that here. The book has kind of given us a graph of like, let's say a person just starts flipping a coin. We can see their first 20 attempts here. Their first attempt, 100% of the time, landed either on heads or tails. And they're looking at heads. So the first time they flipped it, it always landed on heads. So 100% landed on heads. The second time it landed on tails, so 50% landed on tails. Third time it landed on heads, so 67% are landing on heads. Next time lands on tails. That means 50% are landing on tails. Next time lands on tails again. That means you're looking at, what is that? So 67, 50. You're looking at 60% landing on tails. Next time it lands on heads, 50%. Next time it lands on tails. Next time after that it lands on tails. So that means the proportion is a little bit more tails. And we can see here that's clearly like favored towards tails. Every once in a while you get back to that 50-50 for heads, but then it kind of continues being tails, gets closer, goes back to being tails, gets closer. Well, this is if we expand it on the right. Then we can look at our right graph, and this is if we flip a coin 500 times. And what you'll see is like in these first, looks like 100, there's a lot of variability. It's going up, it's going down. We got a lot of tails results, we got a lot of heads results. Well then, as we start going forward, this graph starts congregating more and more towards this 50%. Yes, there is still a lot of variability, but the distance that exists here is nothing like the distance that exists here. It's very, very small. Just like the distance that exists there is nothing like the distance that exists here. It's getting closer and closer. And if we expanded this out, if we took this to 10,000, if we took this to 20,000, we would expect that graph of proportion, we would expect it to get closer and closer and closer to that 50%, or that 0.5 proportion. Every once in a while, it will actually be that 50%. But again, it's not always going to be that 50%. Like, if we're at an odd number, it obviously can't have 50%. Whenever we have an even number, there's a potential for it, but it still might not be 50%, but it's going to be really, really close. We're talking about like a 20,000, the proportion of actual are going to be like 0.505 and 0.495, 0.502 and 0.498, something that's still really, really close to that 0.5, where we can essentially say, over time, it's 0.5. 0.5 of the results will be this. And that's what we call the law of large numbers. So there's no such thing as the law of averages. It's the law of large numbers. And the law of large numbers is this idea that I have illustrated up here. That if we have a probability of an outcome, and it's somewhat predictable, if we do that outcome thousands, hundreds of thousands, tens of thousands, many, many times, this is what the outcome will look like. So it doesn't mean that it can't happen. And it doesn't mean that it can't happen pretty frequently. So it's like with rolling a die. There is a 1/6 chance that it's going to land on 1. And if I roll a die 6,000 times, I would expect somewhere around 1,000 of those to be 1. Not perfectly 1,000. I'm not going to say it's exactly 1,000, but I'm going to say it's probably going to be pretty close to 1,000. If I only roll that die 6 times, it doesn't mean that one of those has to be 1. All 6 could be 1. Like, it could be this really random event where I roll 1 6 straight times. I could roll a die 10 times and I could get 7 1s and 2 2s and 1 3. I might not get 4 5 or 6. In that short run with just a few numbers, it's not going to average out. You're not going to see it end up being those perfect proportions in the short term. Occasionally you might. I could totally roll a die 6 times and then get 1, 2, 3, 4, 5, and 6. That's totally an acceptable result. I could roll a die 6 times and get 6 every time. Really, really small little samples of this aren't going to give me the probability that's perfect. Don't roll a dice, get a 1, and then say to yourself, oh, the 1 is done, so I have to wait for the other. The dice doesn't have a mind. It's completely random. And in those small numbers, it's going to stay random. 12,000 times? Yeah, it's probably going to hit 1 around 2,000 times. It's going to probably be somewhere between 190,000 or 1,900 and 2,100. It's probably going to fall somewhere within those numbers. The bigger and bigger we get, the smaller and smaller those variations are going to be, around that proportion of 1/6. So, definition of probability values. When we're thinking about probability, all probability is measured between 0 and 1. The outcome of probability 0 means that it will never happen. So, there is a probability of 0 that Mr. Yehlen becomes vegan. You can run that simulation 10 million times, and that simulation will never end up giving you something where I become vegan. That is just 0% probability. An outcome with a probability of 1 means that it will always happen. I'm going to do a little bit of a funny joke here. It's like the saying in life, the only thing you can count on is death and taxes. Everyone is going to die. There is a 100% probability that you will die. Nobody knows what age it's going to be. Nobody knows when it's going to happen. Nobody knows all those other factors, but you're going to die at some point. That's 100% probability. And if you're a U.S. citizen, you're going to get taxed. At some point, you're at least going to have to file something with the IRS. Maybe you can get enough deductions where you don't have to pay taxes, but you're going to have to file your taxes. There's a 100% probability. If you're working in the United States, you're going to have to file taxes. And that's just kind of a joke. Make what you will of it. And then any other probability falls in between it. If you have a probability of 0.5, that means if something happens 20,000 times, you would expect around 10,000 of them to have one result versus the other. If you have a probability of 0.3, 10,000 times, you would expect something to happen 3,000 times versus the other at 7,000 times. So on and so forth. Just because you have that probability, though, doesn't mean that it always happens. Let's say that I enter a contest. Let's say that I go through the drive-through McDonald's and there's a contest where 50% of the people who order food win, and I order fries and a drink. That does not mean that one of those things is going to give me a win. It could totally be that I got both wrong. Both of those don't give me a win. I order a drink, I pull off the tab, it doesn't give me anything. I pull off the fries, it doesn't give me anything. That's just the way it is. It's not always, just because there's a 50% chance doesn't mean that it always holds to that. All right, so let's look at our understanding here. According to the Book of Odds website, the probability a randomly selected U.S. adult usually eats breakfast is 0.61. Explain what the probability of 0.61 means in this setting. So this basically means 61% of U.S. adults eat breakfast. That's generally what it's saying. If you were to ask any U.S. adult, do you eat breakfast? Because 61% of U.S. citizens eat breakfast, there's a 61% chance that they would say yes. And that's I don't know. I don't really want to explain it that way, but basically in this setting, it means that 61% of U.S. adults eat breakfast. Now, this does not mean that if we choose 100 adults, exactly 61 of them eat breakfast. That's because we're choosing 100 out of the entire population of the United States. Let's say that I choose 100 and I choose 100 from a group of people who all eat breakfast. I could totally have 100 people eat breakfast. Well, and then in the next group I have more, there are fewer people who eat breakfast. I'm just saying that if I ran this 10,000 times, if I slowly took, if I did 10,000 random questionnaires of 100 people, I would expect the average response of people saying that they ate breakfast to be somewhere around 61. I would expect an average of 61 people if I ran a 100 randomly selected person trial 10,000 times. Doing one trial, I could totally pull 100 people who eat breakfast. I could totally pull 0 people who eat breakfast, 50 people who eat breakfast, so on and so forth. It doesn't mean 61 every single time. It just means that there's a 61 out of 100 chance that each person I ask is going to eat breakfast. And because of that, I'm only pulling 100, I can get results that don't exactly line up with this. But as I expand it, as I ask more and more people, I would expect my proportion to get closer to 0.61. As I repeat this trial of asking 100 people many, many times, I would expect that average of people responding they eat breakfast to be 61%. All right, then we have the probability. It's the measure. Match these probabilities with each statement. The outcome is impossible. It can never occur. That's 0. Mr. Yehlen becomes vegan. It's impossible. It will never occur. The probability of that is 0. Mr. Yehlen suddenly becoming the AP English teacher is a probability of 0. It is something that will never happen. It just can't. The odds are not in its favor. The outcome is certain. It will occur every trial. That's a 1 every single time. So I'm going to go ahead and do a little bit of a flex here, and I'm going to talk about my time rowing. We would get on rowing machines, and we would have a lot of tests, and we would see who's the fastest. Starting in my sophomore year, there was a probability of 1 that I would win the test. There was not a single rowing test from my sophomore year on that I was not the fastest on the team. So probability of 1. Every single time that we stepped on those ergs, every single person knew that I was going to win that event. The probability was 1 that Mr. Yehlen was the fastest rower on the University of Minnesota team from the 2011 through 2012 through 2013 through 2014 season. It was just a fact. If you were to bet on it, you would always bet on me because you knew you would always win. This outcome is very unlikely, but it will only occur once in a while in a long sequence of trials. That's 0.3. Or very unlikely, but it's very unlikely, but will occur once in a while in a long sequence of trials. That's 0.01. So that's the idea of if we did this 100 times, you would expect 1 to work. If we did this 1,000 times, you would expect 10 to work. If we did this 10,000 times, you would expect 100 to work. The best example I can kind of come up with is not quite a half court shot. I think that would be a little bit more, but let's say a full court basketball shot. If we were to just have people line up full court and just heave the ball at the basket, eventually you would expect somebody to make that ball in. And it would happen very, very, very rarely, 1% of the time. It is not going to be common. It would take some skill, things like that. But I could still see people making the occasional full court basketball shot. A lot of work, not happening that often, but you would still just expect it to happen here or there. And then this outcome will occur more often than not. I would say that 0.6 is kind of representing that. This is very vague language, saying it happens more often than not, saying that it's above 50%, and that's all it means. It could also be the 0.99. It's just saying that it occurs way more often than it doesn't occur. In this case, I would say it's 0.6, 0.99. I would say it almost always happens. That would be much more the language you would expect there. But you can make a case for why 0.99 works because you're still saying it's way more likely to happen than not happen. 0.6 just kind of matches with the vague language a little bit more, where we're saying if we did this 10,000 times, we would expect 6,000 of them to work. We would expect 4,000 of them not to happen. So it's happening more often than not. Again, short run versus long run. We cannot push this enough that things can happen in the short run that appear outside the realm of possibility. For example, in roulette, there are the same number of red and black spaces and 1 green space. There's roughly a 50% chance it will land on a black square. Could there be a sequence of red, 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 red? Absolutely. It can absolutely happen. Each one of these things is independent of each other. Every single roll gives you the same 50% chance every single time. Just because it's rolled red 7 times does not mean it can't roll red an 8th time. Now, if we did this 20,000 times, there's no chance that you're going to get 20,000 straight reds. Okay, well, I don't want to say there's no chance, but the likelihood of getting 20,000 straight reds is like beyond incomprehensible small. So, like, that's what we're saying. That's what probability means, is when we're doing it at like numbers of 10, 20,000, these really, really big numbers, if you're getting all reds, there's definitely something probably rigged. Now, if you're getting 8, 9 straight reds, that might be rare, but it happens. So, brief little personal story here. When I was 23 years old, so this was perfectly legal, I took a trip to Las Vegas with my friends, and I sat at the roulette wheel because I think the roulette wheel is kind of fun. I was doing kind of well on the roulette wheel. I wasn't really winning any money. I wasn't really losing any money. I was just kind of there. At the roulette wheel, there were 5 straight reds, and I said to myself, I'm going to bet on black because 5 straight reds is weird. I fell for it. I fell for the idea of law of averages, and then it was red again, and I had to walk away from the table because I set a hard limit for myself on what I was going to bet, and I lost that money. And so I learned a lesson that independent probability, just because it's happened 5 straight times, doesn't mean it can't happen a 6th. Just because it happens 6 straight times doesn't mean it can happen a 7th. I walked out of the casino really upset and really frustrated and kind of cursing the universe because how could this happen? At this point, I had not been teaching statistics. I had not been learning statistics. 29-year-old me would tell, I believe I was 24 at the time, would tell 24-year-old me, like, you should have read your statistics textbook earlier in life. You should have remembered all your lessons from high school statistics. Just because it rolled red 5 times does not mean that it is a rigged roulette wheel. I might have said that to myself like 30 times. That is okay. Finally, simulation. So the modeling of chance behavior is called a simulation. We have done a simulation during one of our first classes when we determined it was possible to pick female pilots for promotion randomly, or when we looked at the chance of caffeine raising heart rate when we started looking at like statistical significance. When you look at statistical significance, you're running a simulation. So performing a simulation, you ask a question of interest about some chance process. You describe how to use a chance device to imitate one repetition of the process. Tell what you will record at the end of each repetition. Perform many repetitions of the simulation and use the results to answer the question. So for an example simulation, let's say that I've received a gift of 5, the rest of the thing, I made this a little bit simpler. Let's say that I received a gift of 4 Three Musketeer bars from a friend. I hate Three Musketeers. I'd never eat them. The idea of an entirely nougat chocolate bar is absurd. He decides to give out 4 bars to 4 randomly selected students from his 2 pre-calc A-B classes, and each class has 20 students. All 4 go to students in my E-Day pre-calc class. My F-Day pre-calc class claims that it's rigged. And I clearly have a bias for that E-Day class. I want to defend my honor, so I'm going to bring the case to you guys. I'm going to have you guys run a simulation to see what the probability of the result is occurring. How would you run this simulation? Like, let's say using table D. Easiest way to run the simulation would be assign 0, 1 through 20 to E, and then 21 through 40 to F. You would choose some random line in table D, let's say like line 107, and then you would start looking at two-digit numbers, and you would pick those out. Any digit that fell between 0, 1 and 40 is who that Three Musketeer bar would go to. Any digit above 40, but so between 41 and 99, you would just skip over and then go until you found. And you would run that simulation multiple times, so you would go through. You're not going to do it on the first one. Like, let's say you go through the simulation once, and like the first number you choose is 39. You can't be like, oh, Mr. Yehlen's bias, clearly my first trial, and it happened. You're going to run through this trial like 50 times, 100 times. If we had, with the 7 people we have in the class, I would make each of you run this at a minimum 15 times so I could get above 100, so that way I could see what are the probability, what's the chance of me pulling 4 people from the same class. If you wanted to do this using technology, you would use the exact same numbering, but then you would like use your calculator and go to like random integer. So you'd go to like probability, you'd go to random integer, you would set it between like 1 and 40, and you would want a number of 4, And like, okay, I just ran a trial on my calculator. I got 38, 37, 6, 21. Okay, so clearly this one didn't work. Next one, 17, 30, 2, 14. This one has somebody from F. 40, 9, 32, 39. That was my next trial. 9, 15, 1, 38. That was my next trial. 5, 1, 22, 35. That was my next trial. 3, 29, 1, 17. Next trial. 13, 39, 2, 34. 25, 9, 40, 29. 2, 5, 28, 40, and so on and so forth. And we would build this up. Obviously, right now, I've only done 9 trials. It's not looking like I'm being very fair. If I do my 10th trial, it still looks like I'm not being very fair. Maybe I am biased. I don't know. But we would keep running this trial over and over, and we would see, like, okay, at 10, this is still very small. Maybe, I have no clue what the actual proportion of chances of this are. If I have numbers 4 through 40, what are the chances of me pulling 4 random numbers and all of them being below 20? I don't know what that probability is, but we could run the simulation over and over and over, and if we ran it like 10, 20,000 times, we're going to get pretty close to what is the actual probability of that happening. And if that probability is above 5, it's probably not that I'm being biased. It's probably much more that it just can happen. It might be rare to happen, but it can happen. And if that probability, that's where that statistical significance kind of comes back in. So we've got to check for understanding here, and this is based on the examples in your textbook. So make sure you read section 5.1 first. This is not going to make sense to you if you haven't read first, because I'm basing it on examples in your textbook. So refer to the golden ticket parking lottery example. At the following month's school assembly, 2 lucky winners were once again members of the AP statistics class. This raised suspicions about how the lottery was being conducted. How would you modify the simulation in the example to estimate the probability of getting 2 winners in AP statistics classes in back-to-back months just by chance? So this is, if you recall, there was like 95 students in school, 28 of them took AP stats, and the winners of the parking lots both came from the AP stats course. The book numbered them 1 through 28, and then the rest were 29 through like 95, and then you had those double-digit numbers. You skipped 96 through 00. You didn't count those, and then you just saw what was the likelihood of pulling 2. In this case, if you wanted to do another back-to-back lottery, what you do is you pull your first 2, and then you reset and you pull your next 2. So basically, you can't have repeats for your first 2, but you could then have a repeat. So if your first and third were the same number, that's fine. If your second and fourth were the same number, that's fine. What's not okay is your first and second can't be the same number, your third and fourth can't be the same number. If there's any repeat there, you just have to move on and move to the next one. And you'll basically, every single time you run this, like you run the trial, you see what happened, you stop, you move on, you run the trial. And then you're going to do this, see how many times it happens, gets your probability. Next one, refer to the NASCAR and breakfast cereal example. What if the cereal company decided to make it harder to get some drivers' cards than others? So if you recall, you had 5 cards, each had a 20% probability. Now we're going to have 5 cards. Jeff Gordon's 10%, Dale Earnhardt Jr.'s 30%, Tony Stewart's 20%, Danica Patrick's 25%, Jimmy Johnson's 15%. How would you modify the simulation in the example to estimate the chance of a fan having to buy 23 or more boxes to get the full set? Well, this is where I'm going to assign numbers 1 through 10 to Jeff Gordon, 16 through, or 11 through 40 to Dale Earnhardt Jr., 41 through 60 to Tony Stewart, 61 through 85 to Danica Patrick, and then 86 through 00 to Jimmy Johnson. I'll run that. I will figure out, and then I will assign each number of those cards, and then I will see. This one is a little bit different. Again, we will pull each one and we will count repeats because we're trying to figure out how many boxes it would take to get all 5. So this time we will count repeats and count those examples in, just like the book says, and we will see how many boxes it takes to get all 5 cards, to get a number from each one of those ranges, and we will perform this as many times as it takes to get all 5, and we will write that number down, and then we will do it again, and we will do it again, and we will do it again, and we will figure out the probability it happens, and we'll figure out how likely that is. All right, you guys have a homework assignment. Please reach out with any questions or concerns, and have a great night.